Section 3.3 is on graph sketching, asymptotes, and rational functions. Whenever you hear the word asymptote, an asymptote refers, if it's a vertical asymptote, it refers to a part of the graph. It refers to a part of the Cartesian plane where the graph cannot cross. If it's a horizontal asymptote, it can cross, and that requires an investigation with limits. So for the most part, in this section, we're going to worry about the vertical asymptotes. We may touch on horizontal asymptotes briefly, but vertical asymptotes are the ones that, for all intents and purposes, we investigate the most because they can cause a lot of problems. When you think of rational functions, think of fractions, functions that have a numerator and a denominator. So if you look at this box, a rational function is a function f that can be described as such. F of x is equal to p of x, which is a function, divided by q of x, which is a function. And of course, q of x cannot be 0. That means we have to be on the lookout for particular x values that may cause a 0 in the denominator. For example, vertical asymptotes. If we want to investigate vertical asymptotes for this function here, this is a rational function because this is a function that has a numerator that is a function, and it has a denominator that is a function. There are various ways to find vertical asymptotes. In this case, the denominator, x squared plus x minus 6, can be factored as follows. X minus, well, let's pause for a second. I'm videoing today from my office, and okay, so here we are. If you take x squared plus x minus 6, that can be factored as x minus 2 times x plus 3. Because if you take x minus 2 times x plus 3 and FOIL that, or if you use the box method, you will get x squared plus x minus 6. If you are stumped here and you do not know what happened to go from this statement to this product, I would suggest that you Google or do some YouTube searches on factoring trinomials. That would be a great review, factoring trinomials. I'm going to assume that you can remember this, somewhat familiar with it. And let's focus on that denominator. I have x minus 2 times x plus 3. The question is, what values of x would make the denominator 0 or undefined? Let's talk about x minus 2. If x minus 2 is equal to 0, that would be a no-no, right? Because if x minus 2 is 0, then that means our denominator would be 0 times x plus 3, and that would give us a 0 in the denominator, which is not allowed. So if x minus 2 is equal to 0, then that means x would have to equal 2. We now know that x cannot be 2 because that would cause a 0 in the denominator. Likewise, we know that x plus 3 cannot be 0, which means x cannot equal negative 3. And if you look at the graph, you can see that where x is equal to 2, they have a vertical dashed line, x is equal to 2. That is one of the vertical asymptotes. The other vertical asymptote occurs at x is equal to negative 3. And notice that the graph does not cross those vertical asymptotes. In fact, the function will get closer and closer to each one, but will never actually touch because those are blocked out as undefined x values. In fact, if we look at the commentary below the graph, we can see that the limit as x approaches 2 from the left is negative infinity because if you are approaching -2, I'm sorry, if you are approaching 2 from the left, that means that you are coming in from the left side of 2. So you're moving in this direction. And notice that the closer you get to 2 from the left, the more the graph approaches -infinity. Also, notice that if you approach 2 from the right, that means you're coming in from the right side closer to 2. Notice that the graph is going up to +infinity. And again, the graph will get closer and closer to x is equal to 2, but it can never actually touch the line x is equal to 2, just like it cannot touch the line x is equal to -3. And we have a definition. The line x is equal to a is a vertical asymptote of a function if any of these statements is true. The limit as you get closer to a from the left is infinity. The limit as you get closer to a from the left is -infinity. The limit as you get closer to a is +infinity or -infinity. And they've taken this definition and they have shown us several illustrations that go with that box. In other words, if you look at this first drawing here, notice that our function is in purple and the line x is equal to a is the asymptote, the vertical asymptote here. And notice that the limit as you get closer and closer to x is equal to a from the left goes up toward +infinity. If you look at this second drawing here, the closer you get to x is equal to a, you go down to -infinity, and so on. So go ahead and take a look at the last two, and you will see why those are vertical asymptotes. So let's look at example 1 here. Example 1 says, determine the vertical asymptotes for the given function. Again, we really need to pay particular attention to what is going on in the denominator, because the denominator is going to yield potential x values that are not defined, because we cannot divide by 0. Luckily for us, this cubic is already factored. And we can tell that we have a situation where x cannot be -3, because -3 plus 3 would give us a 0. X cannot be +5, because 5 minus 5 would give us a 0 in the denominator. And of course, x cannot be 0, because that would give you 0 times x minus 5 times x plus 3. And that would give us a 0 in the denominator. So the vertical asymptotes will occur at the lines x is equal to 0, which happens to be the y-axis. Also, x is equal to 5 and x is equal to -3. Example 2, determine the vertical asymptotes of f of x is equal to x squared minus 2x divided by x cubed minus x. If you look at the numerator, if you look at the two terms, you can see that x can be factored out as a common factor. And if you look in the denominator, x is also common in both terms. In other words, we can factor an x out of the numerator. That gives us x times x minus 2, which is the same thing as x squared minus 2x. It's just in factored form. And if you take an x out of the bottom, let me try to write this. I hope this is clear. If I have x cubed minus x, since x is common in both terms, I can factor out x. And that will leave me x squared minus 1. And x squared minus 1 is a difference of squares. And if you have a difference of squares, they can be factored. I would encourage you to Google or perhaps look for some YouTube videos on how to factor differences of squares, because they will creep up from time to time, especially in my math lab. So I have x squared minus 1. I know that 1 is a square because 1 squared is 1. And it will factor to be, let me bring the x down. I will have x times x plus 1 multiplied by x minus 1. So here is our denominator. And notice I can cancel the x's, which leaves me x squared minus 2 divided by x minus 1 times x plus 1. We now see that the vertical asymptotes are the lines x is equal to -1 and x is equal to +1. So let's talk briefly about horizontal asymptotes. Remember earlier I said that if you have a vertical asymptote, the graph can never cross there. And here we have a picture of two vertical asymptotes. Notice that we have one at the line x is equal to -3. And we have one at the line x is equal to 2. But we also have a horizontal asymptote. Notice that the graph can cross a horizontal asymptote. So let's look at the definition. The line y is equal to b is a horizontal asymptote of a function if either or both of the following statements are true. The limit of the function as x approaches -infinity is equal to b, or the limit as x approaches +infinity is equal to b. What does that mean for us in this case? Well, we can tell that as x gets larger and larger, as x approaches infinity, notice that the line is getting closer and closer to the line y is equal to 1. It can cross there, okay? In other words, we could have a situation where the function may actually go down and up, and as it gets closer, as x gets closer to -infinity, it could be tightening up, getting closer and closer to that line. Okay. Horizontal asymptotes of a rational function occur when the degree of the numerator is less than or equal to the degree of the denominator. So notice this function here. The degree of the numerator is 2 because we have x squared. The degree of the denominator is also 2. And it says that horizontal asymptotes of a rational function occur when the degree of the numerator is less than or equal to the degree of the denominator. Since these are equal, then we know that we would have horizontal asymptote there for that function. Example 3 says to determine the horizontal asymptotes of this function here, notice that we have x to the power of 1 in the numerator and x to the power of 1 in the denominator. And since those are equal to one another, then we know that we do have a horizontal asymptote because, again, it says in the middle of the page here, horizontal asymptotes of a rational function occur when the degree of the numerator is less than or equal to the degree of the denominator. Well, they're equal, so that definitely meets that criteria. We have a picture here to the left that illustrates a horizontal asymptote at y is equal to 3. Let's see if we can investigate to determine how they got the horizontal asymptote at y is equal to 3. Since the degree of the numerator and the degree of the denominator are equal, we are going to evaluate the limit as x approaches infinity and look at the limit as x approaches negative infinity. The numerator has 3x minus 4, and the denominator has 1 over x. And we can see that as the limit, the limit as x approaches infinity ends up being 3. Why would it do that? Because if you have 3x minus 4 over x, if you divide the numerator and the denominator by x, then that would end up giving you 3 minus 4 over x. In other words, if you divide the denominator, let me change colors here. If you divide the denominator by x, that gives you 1. And if you divide the numerator, if you divide the first term by x, that leaves you 3. And of course, we would be left with 4 over x. And if x is approaching infinity, that means the denominator here is getting larger and larger. Well, if the denominator is getting larger and larger, then that means 4 divided by that number has to be getting closer and closer to 0. So this begins to zero out, which leaves us 3. So the limit as x approaches infinity is 3. Likewise, if we are approaching negative infinity, we are also approaching 3. Let's take a look at example 4. On example 4, we're given a function. And it says, again, determine the horizontal asymptote. Well, we notice that the degree of the numerator is 1 and the degree of the denominator is 3, which means that the degree of the numerator is less than or equal to the degree of the denominator. That guarantees that we do have an asymptote. And if we evaluate the limit as x approaches infinity, we will see that we have 0. Now, you may want to go back and review some of the rules as x approaches infinity or negative infinity back in one of our earlier lectures. It may have been lecture 1. And of course, the line y is equal to 0 is just the x-axis. So this would be the horizontal asymptote here. And then we have slant asymptotes. We typically do not do a lot with slant asymptotes. And I'm just going to touch on this momentarily. A linear asymptote is neither the vertical nor horizontal, and it's called a slant asymptote or an oblique asymptote. For any rational function of the form f of x is equal to p of x over q of x, a slant asymptote occurs when the degree of p of x is exactly 1 more than the degree of q of x. So if you look at example 5, we notice that the degree of the numerator is 2, and the degree of the denominator is 1, and 2 is exactly 1 more than 1. In other words, we are guaranteed to have a slant asymptote in this case. So how do we find the slant asymptotes? Well, what we do is we divide x minus 1 into x squared minus 4, and we end up getting x plus 1 with a remainder of negative 3. And this is how we would write it: x plus 1 plus negative 3, which is the remainder, over x minus 1. Note that as the absolute value of x approaches infinity, we would have -3 over x minus 1 that would approach 0, and therefore y is equal to x plus 1 is the slant asymptote. Okay. If you're curious about what we did on the previous page with the division problem, you might Google or do some video searches on YouTube for either long division of polynomials or synthetic division. What about asymptotes of exponential and logarithmic functions? An exponential function of this form, y is equal to a times e to the power of bx, as long as b is positive, it will have a horizontal asymptote at y is equal to 0. In other words, the x-axis will function as a horizontal asymptote. And if you recall looking at our growth problems typically look like this. And you may have picked up on the fact that as x approaches negative infinity, the graph does get closer and closer to y is equal to 0. If you look at a decreasing function, and notice in this case b is negative, b is less than 0. If you have a decreasing function, y is equal to 0 is also a horizontal asymptote. In other words, the x-axis functions as a horizontal asymptote. And then we can have the natural log or the log functions, either one. And they have this shape, right? They start very steep and then they level off. Notice that we have a vertical asymptote here at the line x is equal to a, and that occurs because of this shift here. We're taking the natural log of x minus a, and therefore we would have a vertical asymptote at x is equal to a, and then here we have a minus x, and that would give us an asymptote here at the line x is equal to a as well. So let's look at example 6. Find the horizontal asymptotes of 200 divided by 1 plus 25 times e to the power of negative 0.04x. What we want to do here is we want to evaluate, since we're looking for a horizontal asymptote, let's start off by looking at what's happening as x approaches infinity. Notice that in the denominator here, this expression, as x approaches infinity, is getting closer and closer to 0 because our b value here is negative. And if you'll recall, in this section here, if you have a times e to the power of bx, where b is less than 0, then you have, as x approaches infinity, the horizontal asymptote is 0. So that means that the limit, as x approaches infinity, zeroes out this more complex term in the denominator. And since that zeroes out, what does that leave us? Well, that leaves us 200 divided by 1, which is 200. And of course, we now have to change gears and see what happens as the limit approaches negative infinity. Well, as the limit approaches negative infinity, notice that a negative and a negative is a positive. So what does that mean? If x is approaching negative infinity, then you would have e raised to a power that is getting larger and larger, and 25 times that number would have to be approaching infinity. In other words, 25 times e raised to that power is getting larger and larger. It's approaching infinity. Well, if you take infinity plus 1, that's an even larger number. That means that the denominator is getting larger and larger and larger. which means that the overall fraction is approaching 0. Think of it this way. If I have a pizza and I split it between one person, me, I get the whole thing. But if the number of people coming to the party begins to increase, the amount of pizza everyone has starts to approach 0. In other words, if 2,000 people showed up at the party, everyone would get a slice of pizza that would be so small, it would probably be impossible to even lift it off of the plate. Imagine 2 million people showing up to share the pizza, or 2 billion people. So as the denominator gets larger and larger, the overall amount becomes 0. Intercepts. If they exist, so x-intercepts are not guaranteed to exist, but if they exist, they occur at the values of x that make y or the function 0. And usually we have to factor in order to hunt those things out. Let's take a look at example 7. We have here a cubic in the numerator, and we have a quadratic in the denominator. And if we factor, if first we take an x out of the numerator and then we factor, we end up with x times the quantity x plus 2 times the quantity x minus 3. And in the denominator, if we factor that quadratic, we end up with x minus 1 times x minus 2. Remember that intercepts occur whenever the y value is 0. There's nothing we can do to the denominator to make it 0. We do not want the denominator to be 0. In fact, we can use the denominator to figure out where the vertical asymptotes are. Notice that x cannot be 1, x cannot be 2. So if you look at the graph, when x is equal to 1, we have a vertical asymptote there. Likewise, when x is equal to 2, we have a vertical asymptote there. So let's focus on the numerator. What values of x would make the numerator 0? There's nothing wrong with the numerator being 0. Notice that when x is equal to 0, that would give us 0 times x plus 2 times x minus 3. So x is equal to 0 would be an intercept, and it's marked right here on the graph. And if you look at x plus 2, notice that if x is equal to negative 2, that would give us a 0 for y. And negative 2, 0 is marked on the graph here. And then if you look at x minus 3, if x is equal to positive 3, you would have a 0. And that gives us the point 3, 0 here. Just knowing the nature of the graph, in other words, just by spotting the vertical asymptotes and spotting the intercepts, that gives us a lot of information on what the general shape of the graph should look like. I'm going to pause here and do a shout out once again to Desmos.com. If you are very fluid with the TI-84 and you can graph and you can maximize and minimize the windows on the screen and things like that, by all means, I encourage you to use the TI-84. It is the official calculator for most of our math classes on campus. But Desmos is an excellent tool. So if you want to experiment with Desmos, go to Desmos.com and type in some of these functions, and it does a great job of showing you what the functions look like. I have found some limitations with Desmos when it comes to asymptotes, but generally speaking, in my opinion, the application does a great job on graphing functions. Let's look at example 8. This one says to find all asymptotes and intercepts for this function here. Remember that an exponential function with a positive b value, it's an increasing function, right? It looks like this. And notice that it does not have any breaks in the graph. In other words, there are no vertical asymptotes there. What about intercepts? Well, we know that we can set the function equal to 0 and solve for x, and we'll do that momentarily. But first, let's see if we can figure out whether or not we have any horizontal asymptotes. Well, if we evaluate the limit as x approaches negative infinity, we can see that since we have a negative infinity, we would have a limit of 0. Because if you have e raised to the power of a negative value, let's say we have 0.5 times negative 8, for example. If we have 0.5 times negative 8, this would be the same as having e to the power of 0.5 Let me erase that. A little bit of a mistake there. That would be the same thing as having 1 over e to a positive value. That positive value is going to be 8 times 0.5, 1/2 of 8. Well, if x is approaching negative infinity, this begins to zero out. And that would leave us with the -2. So the horizontal asymptote is going to be the line y is equal to -2. Okay, now for the intercept. To find the y-intercept, we set x equal to 0. Why? Because if x is equal to 0, you know that the graph has to cross somewhere on the y-axis because x is equal to 0 for all of these points. And if you plug 0 in for x, you realize that the y value is -1. So the point 0, -1 is going to be the y-intercept. And then to see if there's an x-intercept, we have to set y equal to 0 or set the function itself equal to 0. And if we solve, we realize that the exact value for the x-intercept is the natural log of 2 divided by 1/2, which is very close to 1.386. So 1.386, for all intents and purposes, is going to be our x-intercept. So what have we learned so far? Well, we've learned how to find vertical asymptotes, in other words, zeros in the denominator. We have learned how to find horizontal asymptotes by evaluating the limits as x approaches plus and minus infinity. And then we discovered how to find the y-intercept by setting x equal to 0. And then we learned how to find the x-intercept by setting y equal to 0 and solving. And if we want to review all of that, we have a nice little table here. And I'll just touch on this very briefly because you are college students and I know you can read. Let me change colors here. Let's go to blue. So the strategy for sketching graphs, this is if you're sketching by hand. And again, as much as I encourage you to learn how to interpret graphs and to sketch them by hand, checking your work on Desmos is an excellent way to learn. So I definitely encourage that. One thing we want to find out is, are there any intercepts? Look for any x and y intercepts. Those are typically easy to find. Let x equal 0 and figure out y. Let y be 0 and solve for x. Those will give you the intercepts. Next, look for the asymptotes. To find, here we go again. Pause early. To find vertical asymptotes, we simply look for zeros in the denominator. To find horizontal asymptotes, we evaluate the limit as x approaches plus and minus infinity. And then we could check for slant asymptotes, and that's going to involve using that long division or synthetic division. And again, we will not do much with the slant asymptote. We also learned previously that we can look at the first derivative and the second derivative in order to figure out where the graph reaches maximum and minimum values, typically by setting the first derivative equal to 0. And the second derivative will tell us whether or not the graph is concave up or concave down. And of course, it's not a bad idea to investigate the domain of f. And typically the domain is going to be restricted if there is a danger in having a 0 in the denominator or perhaps having a negative number under a square root. Piggybacking off of point C, we can use the derivative to find critical values. Also piggybacking on C, we can use the second derivative to figure out whether it's increasing or decreasing. We can use the second derivative to find inflection points and to investigate concavity, and then we can sketch the graph generally. And again, there's definitely nothing wrong with checking your work on Desmos or on the calculator. And if you look at example 9 ties it all up. And I'm going to go through this pretty quickly because you can read this and study it. But just to illustrate how you can use the table to do a graph, here's a function. This is a rational function. It's a fraction. And the first thing they want to do is figure out, are there any intercepts? Well, if you let x be 0, you know that y is -2. So the point 0, -2 is on the graph. What about y being equal to 0? If there's nothing we can do to make y 0 because we cannot make the denominator 0 and there's nothing we can do to make 8 0. So the only intercept value that we can find is the point 0, -2. Then we can look for asymptotes. Notice that the denominator here is a difference of squares. And if you factor x squared minus 4, you end up getting x plus 2 times x minus 2 in the denominator. And that means the lines x is equal to -2 and x is equal to +2 are vertical asymptotes. And we can draw those as dashed lines. And then we can investigate horizontal asymptotes if we have a situation where they actually occur. It says the degree of the numerator is less than the degree of the denominator. In fact, the degree of the numerator is 0 because you could think of 8 as 8 times x to the power of 0. So the degree of the numerator is less than the degree of the denominator. And y is equal to 0 is the horizontal asymptote. And we could investigate slant asymptotes. This says there is no slant asymptote since the degree of the numerator is not, since the degree of the numerator is less than 1 degree of the denominator. In other words, there's a gap of 2 between 0 and 2. So there is no slant asymptote there. Notice that the first derivative is given here. And then they went ahead and took the second derivative using the quotient rule. And based on that, they can figure out critical values and domain values. They have a restriction on +2 and -2. Since +2 and -2 would give you zeros in the denominator, you would break up your intervals. And then once you break up your intervals, you can do critical values, you can do test values, and you can determine whether or not the graph is increasing or decreasing. And then if you set the second derivative equal to 0, you can locate potential inflection points on the graph. And finally, you can investigate concavity. How would you investigate concavity? You would take the second derivative at various test values to determine whether or not it's concave up or concave down. And finally, we can sketch the graph. And this is what the graph looks like. Notice our vertical asymptotes here and here. Because those values of x, 2 and negative 2, would give us a 0 in the denominator. Notice that our horizontal asymptote is actually the x-axis, y is equal to 0. And it's concave up on this interval here, because the second derivative would be positive for any values in that range. Over here, it's also, from 2 to infinity, it's also concave up, because the second derivative at any value in that domain will be positive. And then between negative 2 and positive 2, the second derivative for any of those x values would be negative, which means it's concave down. And we know that we do have an intercept at 0, negative 2 here. So using all of those tools, we are able to sketch with a high degree of accuracy what a function looks like. Section 3.4, optimization, finding absolute minimum and maximum values. If you look at a graph, for example, the one that's shown to the right, you will notice that this is a parabola, this is a quadratic, it's concave up. Notice that it has an absolute minimum value. This is the lowest point that you can find for this particular function. There will be no lower point. Now, there are an infinite number of points above it, as we can see. So again, if you can find the absolute lowest point, that is called the absolute minimum. You can also find absolute maximums. For example, if you have a quadratic that's concave down, like this, it will have an absolute maximum. There would be no point higher than that point, hence the term absolute. If you look at this graph here, this is basically an exercise in being able to identify a high point and a low point based on terminology. If you look at this graph, if you look at this point here, at x is equal to c sub 1, this is a low point. Is it the lowest point on the graph? What about here? This is a high point. Is it the absolute highest point? And you can see we have a low point here and we have a high point here. Well, notice that this point on the far right, since the graph is cut off here, I know it's cut off because it has a solid dot there, the graph never goes any higher. So at x is equal to b, that would be the absolute maximum point. Also, our original point at C1 is the absolute minimum point. On this closed interval, there is no point lower than that at x is equal to c sub 1. Now this point here, it's called a relative maximum. And this point here is called a relative minimum because relative to its immediate environment, it is either a maximum or a minimum. But overall, it's not absolute. For example, if you take the tallest student in one class, that student may be the absolute tallest student. But if you bring in the class next door, there may be someone even taller than the original student. So absolute maximum means that for the given environment, it is the highest y value you can attain to. Absolute minimum would be the absolute lowest you can attain to. And you may have several relative maximums and minimums in the interval. Let's look at this definition at the bottom of the page. Suppose that f is a function that has a domain I. F of c, which is a y value at c, is an absolute minimum if f of c is less than or equal to all other values of y on the interval. F of c is an absolute maximum if the y value at c is greater than or equal to all other y values on that interval. And that's exactly what I just said in referring to the graph in the middle of the page. Theorem 7 is called the extreme value theorem. So let's read it. The extreme value theorem. A continuous function f defined on a closed interval must have an absolute maximum value and an absolute minimum value over the closed interval from a to b. If you have a closed interval, now let's look at the graphs above. These intervals are closed because the endpoints are filled in dots, right? They actually close when x is equal to a and when x is equal to b. That applies to both graphs. They are also continuous functions because you can actually trace these functions without having to pick up your pencil, right? So they're continuous and they are closed. Therefore, they do have to have an absolute maximum and an absolute minimum value. That's an important theorem because that guarantees that if those conditions are met, you must have an absolute maximum and an absolute minimum value. Now, you may be wondering, what about a horizontal line that's closed on an interval? Well, if you have a horizontal line, let's say you have a line here. I'll try to make this as horizontal as possible. And let's say you have a closed interval from here to here. Well, notice that it is also not only closed, but it's continuous. Well, according to Theorem 7, it must have an absolute maximum and an absolute minimum value. Well, for a situation like that, every point is the absolute highest and also the absolute lowest. A little tricky there, but we can still use Theorem 7 to discuss extreme values for horizontal lines. Theorem 8 is called the maximum minimum principle, and it says suppose f is continuous, and if it's defined on a closed interval, to find the absolute maximum and minimum values, the first thing we do is we set the derivative equal to 0. Why would we set the derivative equal to 0? Well, look back at the graphs at the top of the page. Is it not true that at all of the high points, the derivative is 0 or non-existent, right? If we look here, the derivative at that value would be 0. If we look here, the derivative would be 0. So we set the derivative equal to 0, or we investigate to see when is the derivative undefined. So that takes care of parts A and B. Once we figure out all of the critical values, we investigate to see the y values at each of those. In other words, we would plug in, let's say, we know that C1 is critical because the derivative is 0 or undefined.
Transition to A lunch.
And if you look at C sub 2, the derivative is 0. That's a critical value. And if we plug in C1 and C2 into the function, we will figure out how high up these go, right? We would figure out the y values for those 0 derivatives. We would do that for all of the critical values, and then we would finally plug in f of a and f of b, which are the endpoint values. Once we do that, we look for the highest and lowest y values, and that will give us the absolute extrema. Let's look at example 1. For example 1, we have f of x is equal to x cubed minus 3x plus, and our closed interval is from -2 to 1.5. The first thing we're going to do is find the derivative. The derivative of x cubed minus 3x ends up being 3x squared minus 3. That's just power rule for each term. And then we look for critical values. Since the derivative is not a fraction and we don't have square roots to worry about, that means it's continuous. And all we're going to do is just set the derivative equal to 0. And that gives me 3x squared minus 3 is equal to 0, solving for x. We end up getting x squared is equal to 1. And therefore, x could be either 1, x can be 1, and x can be negative 1, because 1 squared is 1, and of course, negative 1 squared is 1. So we have critical values at x is equal to 1, and x is equal to negative 1. A word of caution here, this is from years of experience, and I warn my students about this every time I teach this class, and yet they still fall for it. We figured out that negative 1 and 1 are critical because the first derivative is equal to 0. Most of the students in calculus tend to get that part correct. What they forget to do is they forget to look at the endpoint values, and in this case, our endpoint values are negative 2 and 3/2, because that's the closed interval, right? X goes from negative 2 to 3/2 inclusively. What we have to do is we have to figure out where are the absolute maximum and minimum values. All we have to do is plug in each of the critical values into the function. If we plug negative 2 into the function, which is the endpoint on the left, we end up getting 0. So that gives us this point here at negative 2, 0. If we plug negative 1 into the function and evaluate, we get 4. So the point negative 1, 4 would be here. If we plug 1 into the function and evaluate, we get 0. And we will mark that at 1, 0 here. And finally, if we plug the other endpoint value in, 1.5, we end up getting 7/8. 7/8 is less than 1, and we'll put it, say, here. Okay. Now we have the y values to investigate at the critical values and the endpoint values. So the question is this: what is the lowest y value? Well, in this case, we have 2, right? We have 2 values at let's see, let me erase here. We have these 2 y values of 0. Those are the lowest y values we have. What about the highest y value? Well, the highest y value is 4. So there's the highest y value. And if you look at the graph, you will notice that the point 1, 0 and the point negative 2, 0 are the lowest points on this closed interval. If you look at the point negative 1, 4, it is the highest, the absolute maximum. So we have 2 absolute minimum values of 0, and we have 1 absolute maximum value of 4. Let's take a look at example 2. Example 2, find the absolute maximum and absolute minimum values of the function y is equal to 2 times e to the power of 3x on the closed interval from negative 2 to 1/2. Notice that if you have 2e to the 3x, if you have 2e to the power of 3x, this is going to be chain rule, right? Because we don't have e to the power of x, we have e to the power of 3x. And for some reason, my mouse is trying to give me the blues today. This is actually 2 times e to the power of u, where u is a function of x. And we could use the product rule, or we could just say 2 times the derivative of e to the power of 3x. That's going to be e to the power of 3x times the derivative of 3x, which is 3. And then if you multiply 3 by the 2 you end up getting 6e to the 3x for the derivative. And you may recall that if you graph e raised to a power and the b value is positive, remember this graph is always positive, right? It's always above the x-axis and it's always increasing. So the derivative is never 0, which means there are no critical values. But does that mean we can't figure out the absolute maximum and the absolute minimum? Well, of course not. In fact, it makes our work a lot easier. If we have no critical values, the only thing we really have to do is check the y values at the endpoints. So plug in -2 into the function. If you plug -2 into the function, you get about 0.005. And if you plug 1/2 into the function, you get 8.963. So 8.963 is pretty close to the highest value that occurs when x is 1/2. And then you have 0.005, which is very small. In fact, it looks like it's on the x-axis. It's not. If we were to zoom in, we would see that it's just barely above it. But anyway, we can figure out the absolute maximum and absolute minimum values. And again, since we have no critical values to worry about, those extrema occur at the endpoints. Theorem 9, I will confess, is not a theorem that I use very much. It is helpful, so you may want to think about it. I'll talk you through it a little bit here. Theorem 9 is the maximum minimum principle 2. It says suppose that you have a function and the derivative exists for every x in the interval. In other words, there are no sudden jerks in the graph that causes those cusps, those real sharp points on the graph. And suppose there's exactly one critical value. In other words, the derivative is only critical one time. The derivative is only 0 one time. Then at that value where it is critical, it's going to be the absolute maximum if the second derivative is 0 at that point. It's the absolute minimum. Let me say that again. If the second derivative at that point is negative, it's an absolute maximum because it's concave down. Or it is an absolute minimum value over the interval if the second derivative is positive. Remember, if the second derivative is positive, then it's concave up. And I misspoke. I thought this was actually a different theorem. This is actually a very powerful theorem to know. So let me go back and talk about it a little more in depth. Suppose you have one critical value on an interval. So let's say we have a graph and the derivative is equal to 0 only one time in that interval. And let's say that the derivative happens to be 0 at this point here, right here at the top. I don't know what this value is for x, so I'll just say it's -3. Let's say this point happens to be -3, 9. Okay. And again, there's exactly one critical value on the interval. If -3 is the only critical value, all I really need to do is look at the second derivative at -3. If I take the second derivative, remember the second derivative checks for what? It checks for concavity, right? If the second derivative is less than 0, it's concave down at that point. In fact, it's concave down at every point on the interval, which would make this an absolute maximum. The same thing about a situation, let's say like this. Again, I have only one critical value. Let's say it's right here, where the derivative is equal to 0. Well, here the second derivative would have to be positive because it's concave up. So take the second derivative at that c value And in this case, it would be positive. So go back and look at theorem 9, and I apologize. I thought this was actually a different theorem before I got to reading it closer. So look at the second derivative at that one critical point, and that alone will tell you whether or not you have a maximum or a minimum, or actually an absolute maximum or an absolute minimum. Okay, let's investigate a couple of more problems here. Example 4. Find the absolute maximum and absolute minimum for this function here. This is a cubic, and it has a horizontal shift and a vertical shift. And we're just looking for the absolute maximum, absolute minimum values. And notice that we have an open interval here. This is not a closed interval. We have no solid dots anywhere. So this is an open interval. If we take the derivative, we end up getting 3 times the quantity of x minus 2 squared. All we have to do is figure out when is the derivative equal to 0. The only way the derivative can be 0 is if x is 2. If x is 2, then we know the derivative is 0. That is the only critical value. And that's what makes the previous theorem so powerful. Since x is equal to 2 is the only critical value, I'm going to investigate the second derivative at 2. If you take the derivative of the first derivative, that would give you the second derivative, which is 6 times the quantity of x minus 2. And if you plug 2 in, you get 0. Well, that's not good, because the maximum minimum principle 2 says that if the second derivative at the critical value is positive, it's concave up and a minimum. And if the second derivative is negative, it's concave down and a maximum. Well, here the second derivative at the critical value is 0. So what does that mean? It means that we cannot use maximum, minimum principle 1 because there are no endpoints. We said that earlier. Using the first derivative test, we can see that the first derivative is never negative. Thus, y is increasing everywhere except at x is equal to 2. There is no maximum or minimum values. In other words, this graph, starting on the left, since the first derivative is never negative, it's always going to be either positive, which means going up. It may hit 0, which it does momentarily at 2, but then it continues to be positive as x approaches infinity. So there are no maximum, no minimum values for that function. Now let's look at a word problem. Example 5. This is a business problem looking at minimum average cost. The cost of materials C in dollars to produce X dozen birthday cakes at Yum's Bakery is given by this function. So you tell me how many dozen birthday cakes you want. If you want 2 dozen, I'll plug 2 in to the cost function, and I will tell you how much it costs to make 2 dozen cakes, or 24 cakes, right? So keep in mind, this is X dozen. To figure out the average cost, you take the overall cost and divide by X, where X is the number of dozen. So let's say you plug in 3 because you want 36 cakes, or 3 dozen. That would give you the cost to make 36 cakes, right? Or 3 dozen. And if you divide by 3, that will give you the average cost per dozen. So average cost is not too bad. Just divide by the number. Just take the cost and divide by the number. Next, I want to know the minimum average cost and interpret the results. Well, the average cost is C of X divided by X. They gave us that in part A. And if we take 0.5x squared plus 40x plus 200 and divide by x, notice that we're left with this after we simplify. Notice that x cannot be negative because you cannot have a negative number of dozen cakes. And in this case, x cannot be 0 because you cannot divide by 0, right? We have a denominator there, so x cannot be 0. So we have to have at least 1 dozen cakes. I guess we can do half dozens and 1/4 of a dozen, which would be what, 3 cakes? So any number bigger than 0 is going to work, even fractions. As much as we hate to see fractions come into the picture, any value of x greater than 0 actually works. And we want to figure out the minimum average cost. What is the least average cost we can get here? To figure out the minimum, we could graph this, right? This is just a function. It has a graph. Since it has a graph, we can look at derivatives. So let's take the average cost and take the derivative. The derivative of 0.5x is 0.5. That's just power rule. Of course, the derivative of 40 is 0. The derivative of a constant is always 0. And then if we do the quotient rule for this last term, we see that the derivative is actually negative 200 over x squared. Let's set that derivative equal to 0 and solve for x. If we do that, we figure out that x ends up being 20. Luckily, that happens to be the only critical value we have. And since that is the only critical value we have, we're going to take the second derivative at 20. And if we take the second derivative at 20, we end up getting 400 divided by 20 cubed. And all I care about is this right here. 400 divided by 20 cubed is actually a positive number, which means it's concave up, and therefore we have found the minimum average cost, which happens to be 60. If you take that 20, the second derivative just tells us that the second derivative is positive. It tells us it's a minimum value, but I need to know what is the minimum value. So take that 20 and plug it back into the average cost, and you will get 60. So the absolute lowest average cost for a dozen cakes is going to be 60. Three point five. 3.5 is optimization, business, economics, and general applications. This is where we take everything that we have learned and we put it into practical application. So there are really no new, there are no new calculus concepts to learn here. We're just taking what we've learned and trying to apply it in the real world. So let's just talk our way through a couple of examples here. In example number 1, we're trying to maximize area. And of course, you need to know the shape, right? If it's a circle or a square or a trapezoid, maybe a kite, something like that, you need to know the formulas, right, to find the areas of those things. But luckily, we have a hobby farm that has 20 feet of fencing, and we're going to fence off a rectangular area for an electric train in one corner, okay, of the display room. 2 sides are up against the wall and do not require any fence. What dimension of the rectangle will maximize the area? Okay, so let's think about this for a minute. Let's say that we have a room. Let's try this again. Terrible sketch, but here we go. Here we have a room, And we would like to put an electric train in the corner of the room. And let's say we're going to put it here. And it says in the problem that two sides are up against the wall and we don't need fencing. In other words, we do not need any fencing on this part and this part. And we know that we have 20 feet of fencing. I'm going to let this amount here be X. And I'm going to let this amount here be the leftover, which would have to be 20 minus X, right? Let's think about that for a minute. If the total amount of fencing is 20 feet, if this is X feet here, this has to be 20 minus X here. For example, if X is 1 foot, then I would have 1 foot going across the vertical and 20 minus 1, or 19, going down. If X happens to be 5 feet, then I would have 5 feet going across the the horizontal, and I would have 20 minus 5, which is 15, going down. In other words, the two numbers, X and 20 minus X, would have to total 20. And here is a better picture than what I drew, but as you can see, the algebra is exactly the same. We have the rectangle, we have the X for one side, and the rest of it has to be 20 minus X. If they had told you that you only had, let's say, 10 feet of fencing to work with, then you would have X and 10 minus X. If you had 100 feet of fencing, you would use X and 100 minus X. Now we're looking at trying to maximize the area. We want the most area we can get in this corner. The most area, right? We want to maximize that area. The area formula for a rectangle is length times the width. In other words, it's going to be the area is X times Y. Remember though that Y is actually 20 minus X, which means that the area is 20X minus X squared. 20X minus X squared is, of course, a polynomial, which means we can graph it. It's going to be continuous. And we know that the smallest side can be 0. That would be kind of silly. And we know that this thing cannot be any larger than 20. For example, if we tried to let X be 21, that would give us 20 minus 21, which is -1 for a side length. So we know we're bound between 0 and 20. We know we're bound between 0 and 20. And let's just do what they suggested in the previous section. Let's take the derivative of the area and set it equal to 0. And we realize that X is equal to 10 is the only critical value. Well, if X is equal to 10 is the only critical value, then take the second derivative. In fact, if you take the derivative of the derivative, which is the second derivative, the second derivative is going to be -2. Well, that's powerful. I wish I'd known that earlier. That means this thing is concave down for all X values, which means if you look at the graph, where X is equal to 10, since that's the only critical value, that gives us 10, 100, and we know it's concave down. Therefore, we have found the maximum area. The biggest area we can generate with our fencing is 100 square feet. And that's going to happen if X is 10. So if I go back to that corner of the room, I would have to let this top piece be 10 because we figured out that X is equal to 10 would be the maximum area. And of course, in this example, this length here, the vertical would have to be 20 minus 10, which is also 10. In other words, we would use a 10 by 10 rectangle, or in this case, a square. Example 2, maximizing volume. Here we have a sheet of cardboard This is an 8-inch by 11-inch piece, and we've decided to cut squares out of the corners. In other words, we're going to take this square out, we're going to take this square out, and this one, and this one. We're going to cut those squares out so that we can fold the ends up to make a box. But we want to find the maximum volume. What's the biggest box we can create in terms of volume if we cut those squares out of the corners? Well, once you cut the squares out and fold the ends together, notice that you have a length of 11 minus 2x, you have a width of 8 minus 2x, and the height of the box is x. How do we get 11 minus 2x? Well, I know this whole bottom here is 11, but we subtracted off 2 x's. So that left me 11 minus 2x here. And on the other side, we had an 8-inch box, but we cut those x's off. So that's going to give us 8 minus 2x for that dimension. And of course, the height is just going to be x, because once we fold it up, right, that would be the height of the box. The volume formula for a prism is going to be length times width times the height. The length times the width times the height. So there's the volume formula. And again, we are trying to maximize the volume. We can actually graph this function to look for the highs and lows. I would probably type that function into Desmos and use the graph to get my answer, but let's not do that yet. Okay. If we take the volume function that we start with, if we take length times the width times the height, if we multiply 11 minus 2x times 8 minus 2x times x, this is what we get. This is the volume function. You tell me what x is, where x represents the side of each square. You tell me what x is, and I'll tell you the volume of the box. Well, notice that the domain is between 0 and 4. The smallest volume you can have for the box is 0, right? You can't have a negative volume. And we also can't have negative side lengths. And if you look right here, if x is equal to 4, you still get 0, but if x is bigger than 4, you get negative, right? You would get 8 minus a number bigger than 8. That can't happen. So the domain is between 0 and 4. But if you use 0 and 4, the volume is 0. Well, that's not good. We're trying to maximize. So what do? Okay, we're going to set the first derivative equal to 0. Set the first derivative equal to 0. And we're going to look for critical values.
Okay, we're going to transition A lunch back to third block. Transition back to third block. We'll call for B lunch when the cafeteria is ready. Thank you.
If we set the first derivative equal to 0, this is not going to be factorable. We cannot factor this using traditional means, I should say. So we have to use the quadratic formula. So you may want to Google quadratic formula, maybe go to YouTube and look for some examples on how to solve using the quadratic formula. But anyway, if you use the quadratic formula to solve for x, we end up getting these two answers. One of the answers is 76 minus the square root of 1552 over 24, which is about 1.525. And the other part of the answer is the 76 plus the square root of 1,552 all over 24, which is about 4.808. Those are going to be our critical values. Let's take the second derivative, because the second derivative will tell us about concavity. If you take the second derivative and you plug in the first critical value, 1.525, we get a negative answer. If the second derivative is negative, that means the graph of the function is concave down, which means you have a maximum point. Okay, Let's see what the author says at this point. Since we have already determined that both x is 0 and x is equal to 4 give 0 volume, then we can conclude that 1.525, v of 1.525 must be an absolute minimum. Okay, why did they use 76? Why did they use the 1.525? Why did they not plug in 4.808? That's critical. Why did they not use that? They got two critical values here, but yet they only chose to use the first one. They used the first one and found out that the second derivative is negative, which means it's concave down. They have found the absolute maximum there. But what about 4.808? Let's go back and look at our domain. Isn't it true that the domain is restricted between 0 and 4? In other words, x cannot be larger than 4. If you were to plug 4.08 in, let's say right here, then you would have a negative length on that box, and you can't do that. So 1.525 is going to give us our only critical value in the domain. We know it's a maximum, and if we plug that 1.525 back into the volume amount, the volume equation, or the volume function, we see that a little over 60 cubic inches is going to be the biggest box you can make with that piece of cardboard. This last problem that we're going to talk about is actually one of my favorites. If you think of a cylinder, think of maybe a soda can, or as we say in the South, a Coke can. But a cylinder is shaped like this. And if you took a cylinder and you were to cut down the side of it this way and then roll it out like a scroll, you would see that the sides of the can actually roll out to be a rectangle. And then of course you have a circular top, and you have a congruent circular bottom. In other words, we can take that three-dimensional figure and we can actually flatten it out to two plane figures, right? The circle and the rectangle. So let's go back and see what we're trying to do here. In this case, we are trying to minimize the cost. Okay? Obviously, if you are going to create cans, let's say that you're in the soup business or something like that, or the cola business, obviously you are going to have to pay to create the cans, right? You have to buy the aluminum, you have to pay the employees and so forth. And they figured out, they used a spreadsheet to sort of try to figure out the minimum cost. Well, we can do it another way. If we look at the given information, it says the side of the can when disassembled is a rectangle of area 2 pi RH. 2 pi RH. Why is that? Well, if you look at the distance around a circle, the distance around the circle is called the circumference, and the circumference is 2 pi r. You could also use pi times the diameter because 2r is equal to d. But the distance around the circle is 2 pi r, which means that the distance from here to here along the rectangle would be the same, 2 pi r, and of course the height of the can is just h. That's sort of the trick. Once you figure out that the circumference of the circular bases is actually equal to the length of one of the sides of the rectangle, that is really half the battle. So the total cost of the material...
Teachers and students, please pardon this interruption. Teachers, if you have not shown...
Okay. So that's half the battle. Of course, it says the total cost of material for one can is given by this equation here. In other words, you have to pay a certain amount for pi r squared, which happens to be the circular part, right? You have to pay for the top and the bottom of the can. You got to pay for that part. Then, of course, you have to pay pi RH. You got to pay for this part of the can as well, right? So we have to pay for those three parts of the can. And we know the volume of the can is the area of the base, pi r squared times the height. And what they decided to do was they looked at the cost equation. And if you take the derivative of it and set it equal to 0, you can figure out the critical values. So they take the derivative, they set the derivative equal to 0. Now we're not solving for pi, because remember, pi is a number. We're solving for r. And the first thing they did was they simply took this term here on the left to the right side and made it positive. And then they just used algebra to come to the conclusion that the radius would have to be 4.21. So 4.21 ends up being the only critical value. And if you take the second derivative, this is the second derivative equation. If you plug that 4.21 into it, you see that the result is positive, which means it's concave up, and we can see on the graph that it is concave up. In fact, that second principle that we talked about would say that that being the only critical value, not only is it positive and concave up, but that makes it an absolute minimum. So we have found the absolute minimum for the radius of the can if you want to achieve the lowest cost. So if you're going to go back and you're going to create this aluminum can and you want to minimize the cost based on the information that they gave us, you need to make sure that the radius of the can is about 4.21. So the distance from the center of the circle to the edge would be 4.21. So as you can see, we can use the first derivative test, the second derivative test, our knowledge of graphing with asymptotes and so forth. We can use that information to solve word problems, and these are the very types of problems that engineers deal with on a daily basis. Thank you.